academic researcher and industry consultant for characterization and monitoring of both near-surface and reservoir application. Her presentation title today is Monitoring Velocity Perturbation Using 4D Seismic Data. So with that, I would like to turn it to Maria to start the presentation today. Thank you.
Okay, thank you, Salah, very much for the introduction. We will go through this presentation and I can take your questions at the end. I hope you will enjoy it and hopefully you learn something from it. Maybe I should try the slide view person. Yeah. Okay. So I would like to start with my acknowledgements to Professor Colin Macbeth and the Edinburgh Time-Lapse Project, which is the largest academic research consortium dedicated to 4D seismic, and it's based at Heriot-Watt University. I spent 5 years as a researcher at ETLP, and this is where really I learned all I know about 4D seismic. So in this presentation, I will first present the research incentives in terms of why we're interested in understanding the velocity evolution of the subsurface. I will then summarize and present the methodology spectrum for delta V measurement, and also then discuss the applicability of these different methods to oil and gas, carbon capture and storage, and geothermal. And finally, offer some conclusions. So why do we need to know the changes in seismic velocity? What is their significance? So the first reason is they are key attributes, right, of the subsurface, because change in velocity is related to changes in pore-fluid properties within the reservoir. And that has to do with changes in saturation, changes in pore pressure, and or temperature. And what is really the most common approach is this concept of fluid substitution. So you presume that your subsurface is made up of your rock matrix and then some pore fluids. And what changes during the evolution of a reservoir is really the what you have in these pores. So what you would do is, typically you would estimate properties for your matrix material, and then and also properties for your fluid, and from that you could deduce your saturated bulk modulus and also your dry shear modulus. And your fluid modulus would be a function of saturations. For example, here we have a system of water, oil, and gas. And this is a case where we're assuming a harmonic average of individual moduli. And the same you would do for the density, for example. So here you have the density of your fluid, again, a function of the saturations and the individual densities of your water, oil, and gas. And if you have an understanding of the monitor conditions, you would know, okay, this is how much I expect my water saturation to change, my oil saturation, my gas saturation. So I can predict the updated fluid modulus, insert it into this equation, and now have a new saturated bulk modulus. So of course, all this is unknown in the subsurface. So really what you're using is the link between the moduli to velocity to infer these different saturations, as well as pore pressure and temperature. So the second the second way we can have changes in velocity, aside from changing the fluid that is in the pores, is through geomechanical changes. So imagine you are at a reservoir and you're extracting oil via pressure depletion. So what happens to your reservoir is your reservoir will compact, and that will cause a stress-strain redistribution. And what will happen is your overburden will expand in response to the reservoir compaction, as well as your underburden. And of course, this is, you know, a quite complicated physical problem, but we can make some approximations between changes in velocity and changes in changes in velocity to changes in layer thickness. I mean, this is a very simplistic equation under very particular conditions of uniaxial strain, which means in this equation we are ignoring, for example, stress arching. We are assuming, you know, that the reservoir is infinitely large laterally. But just to see here, this is your vertical strain, and it's related to your uniaxial compressibility times your change in pore pressure. So here I'm just showing an example from the Valhall field, which is one of the oil fields, a pretty old oil field in the Norwegian sector. And it went into production in 1982 and is expected to remain running for a few more years. So this is one of the first cases that was studied in terms of its strong geomechanical behavior. And what was noted by these researchers is there is a correlation between changes in volumetric strain from geomechanical modeling to the observed two-way time differences between baseline and monitor. So I will go later on in this presentation into more detail of, you know, the links between changes in velocity and time shifts. But just appreciate at this stage this correlation between strain and volumetric strain and changes in two-way time, which reflect changes in velocity. Now, if I show these changes in a schematic way, so what we expect from, for example, in a case of, it could be a hardening because of water replacing oil. So this is on your left, you're seeing an example of changes in pore-fluid properties within the reservoir. So this results in a hardening, so positive velocity change within the reservoir and nothing happening in the overburden and the underburden. And on the right, you see the velocity, the schematic velocity response from geomechanical changes resulting from reservoir compaction. So here your reservoir is compacting, and this leads to extension in both your overburden and your underburden. So just a note here that when we are aside from the polarities and, you know, the relative magnitudes, another thing to note between these two different sources of delta V is that the changes due to these pore-fluid properties tend to be more localized, whereas the changes in velocity due to geomechanical changes will have like a more low frequency effect. And they are present over a larger spatial domain. Now, the second reason we are interested in monitoring velocity change is we really need to know the new velocity in terms of improving images, not image beyond 3D. So improving image quality in a 4D sense, which would allow us to do proper quantitative 4D seismic, okay? And as you all know, when you do seismic imaging, you have two interdependent steps really. So you have, on the one hand, you have velocity estimation, and on the other hand, you have migration. And we all know that proper velocity estimation is impacting the migration. You cannot migrate your data unless your velocity model is a proper one. And intuitively, when I first started looking at this problem, I thought, well, if you are looking at 4D seismic, which means you're going to be comparing a baseline seismic data to monitor seismic data, and really you're looking at differences, I thought, well, maybe image quality won't matter as much for 4D, given that, you know, whatever error in migration in the baseline and error in the monitor may potentially cancel out. And it turns out it's if not as much important, it may even be more important for 4D if you want to do proper quantitative 4D. And in this diagram, I'm showing in this figure, I'm showing an example from the Bragg fields, where the authors have done are comparing a map of 4D differences. So these are differences in amplitudes between baseline and monitor. And what they've done here is they've used pre-stacked time migration. And in this second image, they've used pre-stacked depth migration. And the authors commented that the second image made much more sense from a reservoir engineering perspective and a geological perspective. And the reason that they explain is that because the PSDM uses a more accurate velocity to do the migration. So just to say, when we're looking at the problem of 4D imaging, if there is anything wrong with migration, we express this as a time-lapse noise. So typically what you would do is you have your baseline and monitor, but you migrate both volumes with the V in baseline, the velocity of the baseline. And what happens if you then convert your data to the image domain, there will be a mismatch, right? Because we know that the monitor has a different velocity. So if you migrated with the velocity of the baseline, it will appear at a different location in the depth domain. But there is no way to migrate the monitor data from the beginning because with the correct velocity, because that's exactly what you're trying to find. So it's almost like a chicken and egg paradox. So, you know, you're trying to extract the velocity change from 4D, but at the same time, you're saying you cannot have a proper 4D unless you know the proper velocity of the monitor, which you're trying to extract, okay? So that's an impossible problem. So how would you go around that? So the idea is, okay, let's start with our different baseline and monitors. Let's migrate them all with the same velocity model, the baseline model, and then we come up with these quantitative 4D estimates. And those might not be the exact proper 4D, but they're close to the real 4D response. And we can use that 4D response, let's call it the 80% 4D, to deduce the change in velocity. And we can use that change to velocity to now update our migration. So we go ahead with a new migration that has a different velocity for each monitor, for example. And that leads to an improved 4D. So in theory, you can do this in an iterative way. And at some point, you know, if you keep doing that, you're really not going to improve your 4D much because you've reached, let's say, the limit of updating your velocity. The problem with this recipe is that there are two reasons. One is it's computationally expensive, and the other thing is there is also, in all these steps, even though they are semi-automatic, there is some human effort involved in supervising all these algorithms. So we want something that is more efficient. So just to show you an example of this improvement that can be achieved in 4D, quantitative 4D signatures from improving the velocity of the monitor, is this example here from Chen et al. And they have here the 4D differences using VBase for migration of both the baseline and the monitor volumes. And what they have here is a very strong 4D response at this reflection event. But if you notice, this is changing with, the timing of this reflection is changing with offset, okay? Now what they did is they essentially updated their migration with a proper velocity model. Let's call it V perturbed. And what they showed was that the size, not only the seismic reflection event is now flat, but also its 4D amplitude is changing. And even though, you might think, oh, that's better, I can see it better, but really, if you're trying to use this amplitude quantitatively and deduce, for example, how much saturation, how much oil you have, how much water you have, that's the amplitude you should be looking. That's the real 4D response. Of course, this whole problem with migration was made worse by the fact that they had this gas solution interval at the top, which was changing between baseline and monitor. So I mentioned I will next present the full spectrum of delta V measurement, okay? And you will really appreciate all the effort, the brain power that has gone into understanding this problem and trying to find from the simplest solution to the most complex solution, and we will be starting with the simplest methods all the way to the more complex methods, and trying to see if where are the limits of each method and when is each method necessary. So we will start our navigation with time shift inversion in the post-stack domain. So this means now you've taken your baseline volume, you've done all the processing, migration, you've stacked it, and you've got your final volume, and you've done the same for all the monitors. And what you're doing next is you're exploring the relationship between velocity change and time shift. So we understand it intuitively, right? Like if you change the velocity, you're going to change your travel time. But what is this relationship exactly? So it's not exactly rocket science. I mean, we can all say, okay, assume you have your velocity of your baseline and your velocity of your monitor. Your time shift will be defined as the travel time of the monitor minus the travel time of the baseline. And you can say, okay, here I have X monitor divided by V monitor. This is actually twice the thickness of your layer, and then minus X baseline divided by V baseline, okay? Now, if it's so simple, why don't we just stop there? And in fact, it works quite well, but it doesn't always work. Okay, so we're gonna try to see why not. So first, let's just say, we derived this this equation here. Of course, we have delta x is an unknown and delta v is an unknown. So what Lander and Stamira suggested, if we have zero offset, we can really write delta t, so this is time shift divided by time, is equal to approximately delta z over z minus delta v over v. But now what happens is when you look at all these problems with under reservoir geometries and typical reservoir engineering constraints, typically the time shift due to changes in layer thickness is much smaller than the time shift due to changes in velocity. Okay, so typically if we don't have a geomechanically active reservoir, we would just ignore this, sorry, where's my mouse? We would ignore this delta z over z. So we could say that I can take the time shift, which is this delta t, and estimate the time strain, which is essentially the differentiating the time shift over a certain window. And that's the time strain over here. And that's equal to minus delta v over v. Okay, so schematically, let's see what this means. So here is an example where we are, we have a geomechanically active reservoir. You know, the overburden is extending, so the time shift is positive, which means that you have a slowdown in the reservoir, then you have a speed up in the, slowdown in the overburden, speed up in the reservoir, and again, a slowdown in the underburden. Okay, and if you differentiate, you can compute your time strain and then equate that to minus delta v over v, so you get your a negative velocity change in the overburden and underburden and a positive velocity change in your reservoir. And in the case of, for example, it could be pressure depletion, so you get hardening because water is displacing oil, you would expect a slowdown in the reservoir. Now, this is very interesting. When you have a slowdown in the reservoir, if you think about it, time shift is a cumulative property. So if your velocity is increasing in the reservoir, then and nothing is happening in the underburden, your time shift will just stay constant below your reservoir. So it doesn't really go back to zero unless you have a change in velocity in the underburden. So again, similarly, differentiating your time shift, you're able to get your velocity change, which is a hardening. Now, this is, of course, what we think happens, okay? And this is now an application in field data. So here you have, this is from an example in the North Sea, where they were injecting methane. And what you have is this beautiful brightening slowdown. So you see like a positive time shift due to injection, and you have this large blob, and then it kind of stays hot throughout the underburden. And when we apply for theta is just delta v over v, when we solve for it, we get a localization within what we interpret to be the reservoir. Great. But we also have these anomalies below, so like hardening and softening signal, which don't really make sense if you know the field and you know the engineering of this field. So Nguyen, who was one of the PhDs I worked with, actually explained that this is all due to time shift measurement artifacts. Now, I mentioned, you know, this recipe of using vertical time shift and computing time strain and then estimating delta v over v, and I said it tends to work okay in some cases, but it doesn't in more complex cases. So why wouldn't it work? Okay, so the truth is, the subsurface looks more like that, right? It's not a 1D problem where, you know, velocity only varies with depth and stays constant in space. So, you know, you have all these complex structure, and at the same time, this is reflected in very complex seismic wave paths. So really, when you're looking at a seismic trace and it's, you know, all the corrections have been done so that it looks as if you had a source and a receiver just at the same location at the surface. Sorry, my mouse. Can't find my mouse. There it is. So you see, it looks like your source and your receiver is just at the same location and energy propagated down. Okay. In fact, you know, this data comes from all these very messy seismic wave paths, and that has implications on the accuracy of inverting velocity, assuming these ray paths were all straight. And finally, just to say that even if you had perfectly flat geology, if you could create a zero offset study where, you know, you could put your sources and your receivers in exactly the same spot, your time shift measurements could still have a funny behavior. By funny, I mean, you know, not observe this very nice theoretical expected behavior. And you have all these effects happening. So if you've heard of 3D tuning, it's when your seismic reflection from the top of a layer and a seismic reflection from the bottom of your layer is interfering. We also have what we call 4D tuning, which are spurious time shifts caused by this movement of top and bottom times of reflections between baseline and monitor. In addition, if you have very thin bed geology, all these short period multiples will interfere differently between baseline and monitor. So you will have an additional time shift due to these short period multiples that are never really removed. I mean, we're doing our best with processing to remove multiples, but if you ask any processor, they will say, well, if they are short period multiples and you have very thin layers, most definitely they're still there even after multiple removal methods. And finally, just to say that time shift estimation as a method, so, you know, comparing the arrivals between baseline and monitor, is a very hot topic in geophysics and not at all a one-way solution. So there are about maybe 40 different algorithms to compute time shift, and they all have their own behavior. And for me, it was interesting that when you discuss to people from different companies and you're seeing the same field and different time shift behaviors from different time shift algorithms, you know, there's this whole debate from each company saying, oh, we prefer this time shift method, or the others say we prefer that time shift method. So it's just varying. And here, just in this figure, you're seeing this case of spurious time shifts I mentioned before. So this is the theoretical time shift we are expecting, so properly a negative time shift. But then in fact, what you have is just below your interface, you're getting a positive time shift, and then different, let's say here you have a smaller than expected and here a larger than expected time shift. And that's all because of interference of reflectors in the baseline and monitor. Now, on top of that, we have to understand that, as I mentioned, there is no zero offset trace, right? So you construct your volume from all these traces that have different offsets. So Lander and Stammeier recognized that, and they said, okay, of course, if this is my baseline and this is my monitor, of course, ray 2 goes through a longer time in the in this velocity slowdown or velocity speed up area. So the time shift here will be more affected than this time shift. So you need to adjust for that. And similarly, there were other studies that looked at measuring time shift in shot gather domain and extracting delta V properly from the shot domain. Now, another thing I want to mention is this effect of complex geology. So in this case, I will just briefly mention the effect of dipping geology in time shifts. And this is from the work of Cox and Hatchell and Hale et al. And what they did was they understood that if you are using the incorrect migration velocity, by incorrect, I mean if you're using V baseline to migrate the monitor surveys, what you're going to get is apparent lateral shifts and altered vertical shifts. So they understood that there is this interchangeability between vertical shifts and lateral shifts. So if you look at this diagram here, what they observed is this was a dipping field, and they looked at time shifts, and they said if you go down dip, then your time shifts estimated are smaller than the vertical time shifts up dip. And the reason for that is that, you know, bad migration causes apparent lateral deformations that are then eating up some of this vertical time shift, so that now you get a smaller apparent vertical shift. And similarly, up dip, you have a lateral shift caused by improper imaging, leading to a smaller apparent vertical shift. So simply because this problem is quite I mean, you wouldn't be able to just see this and know how to adjust your time shifts up dip, down dip, and up dip. They came up with this, I would say, very fair approach, and they said, okay, you know, we understand that field data goes through processing that is not 100% correct because we're using this V-base for both baseline and monitor, but we can just do a comparison with synthetic data that mimics this bad processing. And then if we compare synthetic data with bad processing and field data with bad processing and they match, then we can say, okay, we can now have more confidence in this velocity model. Okay, so the method is you have to assume your change in velocity. You ray trace normally in this new velocity space. You demigrate using the monitor velocity space because effectively you want to have pre-stack data, and then you remigrate using the baseline velocity. Okay, so this remigration step is properly the wrong let's say processing step, and now you compare your synthetic to the observed shifts. So of course, none of this is, it's not really something very practical, but in this case, it was one of the first studies to properly tackle the issues with vertical time shift measurement and in dipping fields. But in any case, their conclusion is that, you know, if you have complex geology, this time strain being a function of velocity change is really not a straightforward relationship. Another, another application that looked at these lateral shifts caused by, I keep calling it bad processing. It's not bad processing, it's just how processing is done because of practical considerations. So if you use the baseline for the monitor surveys and get these apparent lateral shifts, you know, if you want to then come in and take differences between monitors, you need to properly align the two images, right? So this is a case of here in this application, they were not after the velocity per se, they were after lining up images, but in the process of lining up, you can say, well, I had my baseline, I had the monitor, I'm trying to match my monitor to the baseline. If I look at the vertical component of this warping vector, that effectively gives me the correct time shift, okay? And this is what we call the cross-matching and warping procedure. So Hall et al. In this case said, I have my streamer data, and I have these ocean bottom cable data, and clearly I cannot take the differences just like that because of these vertical shifts and lateral shifts. So here you're seeing the same data as here, but now it's been warped. And between here and here, their algorithm also applies local refinement, okay? So looking at this, you would say, okay, perfect, job done again. But then the issue with this method is that this type of algorithm is practical if you're looking at warping very discrete interfaces, which means I'm picking my interface here, I'm picking another interface here, doing the same for my monitor, and I'm trying to match those interfaces. But the issue, and that's what pressed the problem to other directions for solutions, the issue is that you're not just interested in these discrete interfaces. You want to know everything about the velocity changes across your entire seismic volume. Okay, so the issue remains, how could we extend this type of warping into a continuum? I mentioned before this issue of, you know, dipping reflectors, and I want to bring up this other study by Thor et al. 2010. So I mentioned Cox and Hatchell said, if you have dipping geology and you migrate your volumes with V baseline, you're going to have apparent shifts. And that's bad because that will affect your vertical shifts. And that gives you a bad estimate for velocity. So what Thor et al. Said was, okay, let's see if we have dipping geology, but this time if we migrate our monitor data sets with the monitor velocity, so in this sense it's an ideal migration because you're migrating it with the correct velocity, are we going to have you know, like a perfect alignment a perfect alignment in the image domain, number one, and are we going to have 4D differences exactly in the location they are occurring? So what they showed was that even when you have this ideal migration, and this is a synthetic study, so of course they know the perturbed velocity model, what they saw was this very bizarre tail. Okay, so they call it coda. So it's a tail behind the origin of this 4D. Okay, and what they noticed is that that tail wasn't really vertical; it was subvertical and actually perpendicular to the dip. Okay, so what they realized that first to say that this was not present, this wake was not present in the 3D images, but it was only visible on the 4D image. So this suggests that your 4D image is even more sensitive than your 3D image in picking up these artifacts. So seeing that, the idea came to, I will say Pierre Thor, but it's Pierre Thor and some researchers from Total. The idea came that perhaps rather than measuring time shifts in the vertical sense, we should be measuring time shifts perpendicular to dip, okay? So I call this, it's a 1D inversion, right? Because you're you're essentially inverting for velocity from your time shifts, but you're doing that not 1D inversion in vertical domain, but 1D inversion in this 3D depth domain, okay, in migrated data. So this is my name of the method, but in fact they call it warping again. And I didn't want to use it here because warping was used previously by Hall et al. So let's call this 1D inversion in this 3D depth domain. So this is perhaps, okay, the only long equation, and you don't have to worry about it. This is a very well-known 1D inversion for velocity. So this is your baseline trace, and this is your monitor trace. And the interesting aspect in this equation, this is your, your source wavelet, and here you have the definition for N and the definition for W and some additional weights. So this is an improvement over the time shift to change in velocity equation, in the sense that they not only look at the kinematic aspect between baseline and monitor, but they're also looking at the dynamic aspect. So a change of reflectivity between baseline and monitor due to this velocity change in the subsurface. So using this 1D inversion onto this 3D depth time axis, okay, they actually showed that, and this is from a synthetic study, that this is the known true location of the velocity perturbation. This is inverting using this equation, but assuming a vertical ray path, and you see how everything is just smeared. And this is the same equation, but now applied onto this 3D depth time axis, which is actually perpendicular to the dip direction. So pretty good agreement between the true and this improved algorithm, and much better localization of the velocity change. Now, one of the main advantages of this method is that you really apply it to post-stack data, so you don't need to reprocess your data and everything. It's very simple computationally because it involves just this 1D warping, so this 1D inversion plus ray tracing, and they showed it to be great for even very large dips. So in their case, I believe in this example, they said this was a field example, and the dip was 30 degrees, which is enormous, okay? But again, I didn't see much progress into other field characteristics and other complexities of geology. And just to say, this way of measuring time shift perpendicular to dip, in Thor's approach, they did ray tracing and used this normal incidence rays, whereas for Otterber and Agud, they had this method of demigrating to several capture layers and estimating the time shifts perpendicular to dip. This is, for me, let's say, seeing this, I wanted to understand this, and I thought, there must be a way to explain it with very simple algebra. And indeed, if you assume a homogeneous medium, okay, and a dipping reflector, and I can define the angles between the angles of dip in both the time domain and the depth domain. So these T's and Z's are time domain, depth domain, and I can define it for my baseline, and I can define it for my monitor, and I can define it for in pre-migrated data, so those are these thetas, and also for post-migrated data, okay? And in fact, what I showed with very simple algebra is that if you have unmigrated zero offset data, this equation is 100% correct. But then if you have migrated zero offset data, you really should be looking at delta T over T at perpendicular, at a direction perpendicular to dip. Okay, and then in this case, that's equal to delta V over V. Now pressing on, I mentioned the issue with dipping geology, okay? But there was another issue having to do with the seismic rays not being zero offset, okay? And with the fact that potentially in many areas, your velocity perturbation has a spatially limited extent, okay? And this very simple diagram, and in my opinion, always the best, the hardest diagrams are the simple diagrams, okay? And this was done to me at a coffee break at one of the EAG conferences by John Edgar, okay, who had presented his work on pre-stack time shift inversion. And I was saying, well, I just don't understand what's wrong with doing inversion in post-stack data. And he drew this diagram and he said, well, if you have, look at ray 1 in the baseline and in the monitor, and now let's look at it in the, ray 1 in the baseline and ray 2 in the baseline, and let's look at them in the monitor. And obviously here I've simplified things, they're straight and they should be, curving. But in this case, just think about that you're, in this case, in the monitor survey, ray 1 is not seeing this velocity perturbation, but ray 2 is seeing the velocity perturbation, okay? So what if we migrate both ray 1 and ray 2 using this V base over here, okay? If we migrate it, what we will have is, both these rays will be moved to, some location in the midpoint, common depth point, etc. But the issue will be that ray 1 will have no time shift, but then ray 2 will have a time shift. So, you will have this measurement of time shift over here, and you will say, okay, so if I'm doing a post-stack time shift inversion using this trace, I'm gonna position my velocity change in this spatial location. Well, that's not it, right? The spatial location was over there. So what he suggests, so Edgar and Blanchard, was to do pre-stack time shift inversion using what they call velocity change tomography. Okay, so they have this, they parameterize the space into this grid, and they look at all these IJ's cell indices, and then 1 and 2 are your baseline and monitor, and they set up a pretty large, I didn't write it here, a pretty large tomographic inversion to solve for all of these individual slowness and baseline and monitor to properly find the location of, spatially pin down the location of velocity change. So here you're seeing the results of this tomographic algorithm. So this is again a synthetic case, and what they show here is this is the true subsurface in terms of velocity change. So they have a slowdown and a speed up and a slowdown. No, yes, yes, okay. And then what they show is if you do post-stack inversion, this is what you invert. And then if you use their tomographic algorithm, you invert for that. Okay, so two main differences. Spatially, there is better correlation. And the second aspect is the actual magnitude of the velocity change is more accurate. And of course, after this seminal paper, they went on to improve further this algorithm by putting on geological constraints and all types of smoothness business. Now, another method, which comes under the name again of warping, is this what is called the wave equation image warping, and it was developed by Khalil et al. So in this case, what they're saying is, again, you need to be measuring time shifts perpendicular to dip. And the way they are estimating them is they formulate their problem in this image domain equation. So this is the image wave field, and it's a differential equation, and this is the initial condition, and they consider it to be the baseline image, okay? And they're trying to solve for this tau, okay, iteratively to invert for it until both baseline and monitor images align, okay? And in this case, you're seeing their synthetic explanation. So here's their baseline, and they're showing this for different dips. And here they are applying a time shift and consequent depth shift in the image domain. And here they're showing you the estimated normal displacements. So this is what you would have estimated if you were if you were measuring in this direction rather than that direction. And then finally, they look at the difference between baseline and monitor, and this is the difference after applying the estimated shifts. So obviously, if you have aligned them well in the image domain, your baseline and monitor, if you subtract these reflectivities, they will be 0. So this is the end result. So closing now all these methods, I call them in a way, in a nutshell, they are all 1D methods, even though sometimes they go into a semi-3D domain. But now we move on to the next category of in the spectrum of methodology spectrum for velocity change measurement, which is migration velocity analysis. Okay, so this is traditionally, the first step in any type of migration is this MVA, so migration velocity analysis. And really, in this approach, you're really exploiting the difference of image change to in relation to slowness change. So when we look at the time-lapse project, the time-lapse problem, I mentioned before that if you migrate your baseline and monitor both of them with V baseline, you will get a mismatch in the image domain. Okay. So I mentioned in theory, we can we can start with this monitor data set which has been migrated with V baseline. We can demigrate it with this baseline velocity, and then this is essentially undoing the bad processing, and then remigrate it with different delta V's until the baseline and monitor match in the image domain. And this is a perfectly sane approach, but the main issue with this is the speed. So recognizing that, there are all these methods developed essentially to speed up this this process. So, for example, you know, Shores and Nguyen proposed, let's say, demigration, migration with curvelets, and this is a way of exploiting only local perturbations in velocity and offering a computational advantage. And the second one, demigration, remigration in the post-stack depth domain. Again, it's a way to avoid the issue of demigration and remigration in the pre-stack domain. And finally, again, post-migration rate tomography, which which solves which is picking tomographic, which is picking the common image gather and demigrating them, and then solving for a tomographic matrix and looking at how the image, if the image gatherers become flatter, as a way to select the proper velocity model. And finally, I mentioned all these methods above as a way to speed up the process of demigration, remigration, but all these methods looked at only the kinematic aspects. So you're only looking at the effects of velocity in time. But then FOML has another category of migration velocity analysis, which is through velocity continuation, which is now looking at not just the kinematic aspect, but also the dynamic aspect. And this velocity continuation, it's a fairly, like all these methods, there is a mathematical rationale and derivation behind it. But for this approach, they sort of base it on the concept of cascading migration. So rather than doing migration in a big step, FOML is dividing it into smaller migration steps, which if you make those steps to infinity and make each step infinitely small, you are getting a new differential equation that he solves in the time midpoint space, and that's his velocity continuation equation. And then moving on to what is called the wave equation migration velocity analysis. It's another dynamic dynamic approach. So you look at the flatness of your angle domain image gathers as a way to understand if your velocity is correct, and you use the forward operator is something that takes you from changes in velocity to changes in the wave field and changes in the image domain, and the inverse is going from your really understanding and solving for changes in the image domain all the way down to changes in the velocity. And WEMVA was initially created as a 3D approach, but then Schrag and Lumley, they looked at 4D WEMVA, which is now a way to solve for the time-lapse changes in velocity. And finally, again, in this MVA category, we have the image domain tomography. So again, it's a full wave equation solution, and it looks at the correlation between migrated images, so baseline and monitor. And it was one of the main advantages of this method was that it is great for cases where you have very low repeatability between your baseline and your monitor. And just for those who are not familiar with it, so when you're conducting baseline and monitor surveys, you put a lot of effort to deploy sensors and sources at exactly the same locations. This is a case of a method that can address any type of mismatch between sources and receivers. Last but not least, and we can call this the king in terms of this spectrum for delta V measurement, is full waveform inversion. Okay, and I say it's the king because it's the most complex solution and the most accurate under certain conditions, and I will explain. So in a very abstract way, you can think of full waveform inversion as a comparison between synthetic data. So this is your synthetic data, and it consists of a forward model of your model parameters, okay? And in this case, your model parameters are the subsurface elastic properties, and your forward operator is the seismic wave equation. So you construct this synthetic data and you compare it to your observed data, and you do an optimization whereby you try to minimize your objective function. Okay, so in other words, you try to minimize the misfit between synthetic and observed data. And there are all these flavors of FWI: acoustic, elastic, linearized, nonlinear, isotropic, anisotropic, viscoelastic. So the main issue for these methods for many years were two. Okay, so the first issue was computational time. Why? Because for every new model that you assume, you need to compute synthetics, and that takes a long time. And the second issue was that when you look at the objective function, because there are so many unknowns, and you have like a lot of local minima in the objective function, so you might be trapped into these local minima. So just to say how we have overcome these problems is, firstly, computational time is becoming a lesser problem by the day. Okay, so you know, I can even see it in academia. So, you know, what I was asking 5 years ago, and they would say, oh, you know, you have to queue and it will take a long time, and we don't think we can give you all these nodes. And now, you know, they say, oh yes, job done, one day. Okay, so this is very computational time is becoming very cheap. And the second aspect, this convergence to local minima, if you add what we call like smoothness constraints, that you know you cannot have your solution varying so quickly or so much laterally, and also an a priori model. So if you have some understanding of what your model should be, then that acts to stabilize the inversion. So now we can see that it's a fully practical solution, and actually very commonly applied. And here you're seeing an example from Cirque et al. 2010. So this is seismic data that has been migrated through a velocity model from conventional methods. So that would be from migration velocity analysis, and then data migrated from the velocity estimated from this FWI algorithm. And clearly, you know, you see much better continuation of events. You also see kinematically, for example, no sagging where it shouldn't be, and so on. Now, when it comes to time-lapse FWI, again, you have to appreciate this is an enormous large topic. So there may be dedicated sessions for FWI running, for example, at SCG and EAG, and dedicated workshops. But if we look at time-lapse FWI, there are many ways how you can combine your baseline and your monitor data sets and how you can invert for them. So you could do, for example, a parallel difference, which means you are inverting, you're doing FWI for the baseline and for the monitor separately. You could do sequential, so you do your FWI for your baseline, and that velocity acts as a starting model for your monitor inversion. Or you could do like a double difference. So you have the model parameters of multiple vintages into your objective function, and you're trying to minimize them. And it seems, again, like there are dedicated studies that compare different methods, and it seems that the sequential difference was more robust. And then further ways to do it, so for example, simultaneous inversion, where you invert for baseline and monitors simultaneously, or you cross update, so you do sequential first and then use the monitor as a starting model for the baseline, and all sorts of way to combine them. And further to that, you can have FWI combined to other methods, so tomographical methods, to decrease the computational costs. And I will close the methods with a fairly newer method that I am actually very curious to see how it's applied further to time-lapse data. So this is joint migration inversion, and it's been developed primarily from the Delphi group in Holland, and it's again the forward modeling is again full wave field modeling, and it incorporates migration as well. And the input parameters are velocity and reflectivity. And of course, if you have velocity and reflectivity, you can solve for your density. But what I like particularly about this method is that the multiples are included, and this means that rather than trying to remove them from data, you can use these multiples to improve illumination. And of course, there are quite a few similarities to FWI. Again, you have, if you are more familiar with inversion procedures, you have, again, like an optimization based on your model gradients. But then the main difference to FWI is that you're including multiples. And here is the main equation, and again, is just your synthetic data and your data observations and your model observations, and you're trying to solve the optimization problem in a least squares sense. Now, when they've applied joint migration inversion to time-lapse, they call it simultaneous JMI, and then the objective function becomes much more complicated because they add in the monitor survey into the objective function. So here is an example where they've inverted for the velocity, and here inverted for the reflectivity. And again, what is particularly useful is that this method works very well even for data sets where we have low repeatability, so differences in the locations of receivers and sources. So now that we've finished this whole navigation of different methods, you may say, okay, what do I use, and you know, where do I start with? And I think it's safe to say that you know, starting with the blue low level calculations and perhaps low level precisions is the the best way, because that always provides you some QC for when you go into more complex methods. And at the same time, you have to evaluate what are the physics of your problem. So is your velocity very complex? Do you have large dips? Do you have thin layers? Do you are your surveys very repeatable, and so on? And also, finally, you know, what are your computational what are your computational resources, and do you have that data? Because, for example, you might be, for example, at ETLP, most of the data we got from sponsors were actually in the post-stack domain, and then we had to ask for some pre-stack data, but they were always already migrated. So going into these more complex methods means you also need to deal with much larger data volumes. So you have to be to have the resources for that. Now, in terms of the applicability of these methods to different applications. So obviously, these methods were developed for oil and gas applications. But if we were to look at CCS scenarios, in a way, I think it's safe to say that most of these methods will work great, because in many ways, CCS is an ideal for this scenario, because typically you have a very strong signature from your injection. The main issues you may have to address in terms of 4D seismic with CCS is that, you know, given that you want to monitor these plumes for a very long time, you have to look at seismic acquisition considerations, geometries, and so on. So potentially, you know, whether you can have repeated or permanent sensors or not, that will affect what type of method you will use. Another aspect is that unlike oil and gas in CCS, we're also very interested in the near surface in terms of identifying potential leakage paths. And then the last thing for CCS is, I think we need to work more on quantitative interpretation, because it seems, you know, all types of simulator to seismic and different types of softwares, they're geared towards oil, gas, water systems under certain temperature conditions. So in CCS, you know, you might have supercritical conditions. So you need to make sure you're choosing the appropriate physics for that problem. And now, when it comes to geothermal, and this was a short discussion I had with Hamid Sarouche at the beginning of the talk. I think I would really like to see more 4D seismic applied to geothermal. And of course, before you apply it, you want to test the feasibility. But from my perspective, there are a lot of similarities to oil and gas in terms of we have this need to define the subsurface characteristics for fluid and thermal flow. But at the same time, we have many differences to oil and gas because the physics of source extraction is different. The geological medium may be different, and the economics of development is different. So, for example, you know, in geothermal, it's not the sweep you're looking at, but rather you want to track the thermal front and understand the changes in temperature in the subsurface. And just to say what I saw in the literature in terms of seismic applications applied to geothermal, those were mostly for 3D characterization. And then when I look at published monitoring seismic applications, they are primarily via induced seismicity. So you'll use the micro events to look at velocity and Q factors and focal mechanisms and infer geothermal properties. But the issue with that is that your induced seismicity is it happens outside of your control. Like you, the location and time is because of the system. So I think I would be more comfortable with the method that I can design to happen every at a certain rate and at special locations. Now, what of course you will hear from most industry partners perhaps is that, well, you know, geothermal may not be as good of a product in, you know, using such a complex and expensive technique as 4D seismic may not be necessary. But I just want to remind everyone that this is the exact dilemma that the oil and gas industry faced when people started introducing 4D seismic 20 or 30 years ago. People thought 4D seismic is too expensive for oil and gas, and yet it proved its value. So I think what we need to do to get oil and gas on the geothermal exploration projects is to really work on feasibility studies and also look at integrating 4D seismic with other geophysical methods that are very sensitive to thermal properties. And finally, look at the integration with reservoir engineering. So just to conclude, I have no idea what time it is. So I want to say we are interested in time-lapse velocity for two reasons. The first is it's a geophysical attribute we want to quantify. So it tells us things about the pore fluids. It tells us things about geomechanics. And the second reason is we need a better velocity estimate throughout time to get better image quality in a 3D and 4D sense, as well as quantify better the 4D response. I presented to you a very long and maybe boring discussion for this very broad spectrum of methodologies for delta V, and really they are so some of them are so complex and involved that I may have not given them enough merit. But just to summarize, you know, we have these simpler time shift methods, and then going to the migration velocity analysis family, full waveform inversion, and joint migration inversion. I explained that, you know, we can start with these simpler methods, but then we may have problems due to dipping geology, where we're assigning the proper location of delta V, these spurious time shifts, interference due to thin beds, the robustness of some time shift methods. But for many applications, these very low cost, low effort solutions work great. And if they don't, they can be considered a great starting point or your 80% solution. And finally, I think we can agree that velocity estimation methods can be applied to CCS quite in a very straightforward way, and they have been. But for geothermal, we have more questions to answer and to prove that there is value to be had. So with that, I would like to thank Dr. Hamed Sorish for inviting me to give this talk, and Petrolern for organizing these events. And thank you to all the listeners. And just to say, this is where I'm Skyping from, not these beautiful buildings, somewhere more inland, but it's this tiny fish village in Scotland. So thank you.
Thank you so much, Maria, for this nice and thorough presentation. We might have time to take one or two questions. Let's see if we get any from participants. Yes, we got one from Masood. Masood, I'm going to unmute you, so please go ahead and ask question. Hamid, I think you have to do it because you are the host here.
I did. You can go ahead and ask.
Okay. Hey everyone. Thank you, Ahmed and Salah. And hi Maria, it's nice to see you. I'm really thankful for this great presentation. You proposed and share with us lots of methodology. It was interesting. I have just one question, and because you have a really great experiences in this field, and I would like to see the possible relation between the slide number 25 and 15. In the slide number 25, you show a great example about that the variation of the time shifts in the horizontal way. But I was thinking about, is it possible to see some kind of these variations in time shifts in the vertical way? Imagine a scenario that we have a deep reservoir, it's not a thin reservoir, and we have an injector. So the perforation of injector is, you know, that is different. And we could see the effect of the pore pressure increases, the softening effect, water saturation increases, hardening effect. And maybe if we go to the deeper part of the perforation of injector, for example, near to the aquifer, it's possible that we could see the effect of the salinity changes, the softening effect that the injector water is pushing the aquifer. So we could see different level of time shift, different level of velocity changes at different level of the depth. So that's the reason I was thinking about the slide 15 that you show, or maybe 14, yeah, the 14, that you show that about work of your PhD student, that there are some, okay, 15, yeah, there are some side lobes or noise that they consider about the time shift estimation. So I was thinking about that, is it possible that we could see time shift analysis at different level of the depth? Because what we see usually is the time shift that coming from the reservoir at the base of the reservoir, but is it possible to see the softening and hardening time shifts at different level of the depth?
Okay, thank you for your question. So when we look at time shift, okay, and maybe this is the best diagram to show it. I mentioned that time shift is a cumulative property, right? So, you know, you have this velocity change, and that takes your, you know, you have a time shift increase, and then you know you have an opposite switch in polarity, so that now you have an increase in velocity, so your time shift is now moving that way. So in theory, when you're measuring time shift here, okay, it's okay, the slope is following that velocity change, but the magnitude is affected by this time shift, right? So it's not a case, if I may insert a, so if this is your time shift up to the reservoir, you know, your new time shift is not doing that. You know, it's following from your previous time shift measurement because of this cumulative effect. And then when you differentiate it, and this is what essentially Fong has done. So she took the time shift and estimated the time strain here. Essentially, she undoes that accumulation, right? So she's able to separate different zones of velocity change. So to answer your question, yes, if we have a velocity that is not just localized in one area vertically, but we have a full profile of velocity changes, we should be able to properly extract those from the time shift measurement. It's harder to interpret these from just the time shift, because obviously time shift, as I mentioned, is a cumulative property. So your whatever you're measuring down here is affected by what's up there as well. But by taking this differentiation, you're undoing the effect of your top. Okay, so it's essentially you're doing a layer stripping approach to evaluate your your velocity changes in a depth step manner. Okay, what I explained in slide 26 was slightly different, and it had to do with your velocity change being spatially limited, so that when you compare different traces that would normally be stacked after processing, some of those traces will have the time shift and some will not, and these traces that would be collapsing, you know, to this location would exhibit time shift, and we would interpret time shift occurring right beneath the location of the trace, but in fact it would have been laterally displaced at another location. I hope I answered your question.
Thank you, Maria. Do you have any other question or follow-up from Masoud? I think we're good here at 12:30 in Central Zone. So thank you so much, everyone, then for joining us today, and thank you so much, Maria, for giving this nice presentation.
And sorry for going over time.
Oh, that's fine. It was
Thank you very much.
Thank you for doing that. Please make sure you follow us on LinkedIn to receive updated information about past talks. With that, you all have a good day. Thank you.
Thank you. Thank you very much. Bye-bye.